Okay, today we're going to have a look at chapter 6, gravitational fields. There are two topics we're going to have a look at. They are Newtonian gravitation and orbits. We'll spend one lesson to talk about these two topics. So early in the formation of our galaxy, tiny gravitational effects between particles began to draw matter together into slightly denser configurations. Those in turn exerted even greater gravitational forces, resulting in more mass joining the newly forming structures. Eventually, those repetitive and continuous gravitational effects formed and shaped our Milky Way galaxy, as shown here in Figure 1. The same process of gravitational attraction on different scales accounts for overall structure of the entire universe, despite being the weakest of the four fundamental forces. Gravity accounts for how the planet in our solar system move and orbit around the sun. By the late 1700s, scientists had identified all the inner terrestrial planets, as well as gas giants, Jupiter and Saturn. Then British astronomer William Herschel used observations of the relative movements of the stars to determine that a presumed star was actually an additional planet. The new planet was Uranus. Scientists then observed that Uranus' path was anomalous. It seemed to respond to the full another distant but unknown body. Using mathematical analysis, scientists predicted where the unknown body would have to be and began searching for it. In 1846, scientists discovered the planet Neptune, which is shown here in Figure 2. So the force that causes Uranus to wobble slightly in its orbit is gravity. Same force that causes Earth and other planets to revolve around the sun. To revolve around the sun. Sir Isaac Newton, whose laws of motion provide the foundation of our study of mechanics, used known data about the solar system to describe a system of physical laws that govern the movement of celestial bodies around the sun. Through this inquiry, he formulated the universal law of gravitation, which states that there is a gravitational attraction between any two objects. If the objects have masses m1 and m2, and their centers are separated by a distance r, the magnitude of the gravitational force on either object is directly proportional to the product of m1 and m2, and inversely proportional to the square of r, which is shown by this formula here. Fg, which is a magnitude of the gravitational attraction, equals uppercase G times m1, m2, divided by r squared, where uppercase G is a constant of nature called the gravitational constant, which is equal to 6.67 times 10 raised to the power of -11 Newton square meter per square kilograms. So Newton's law of gravitation plays a key role in physics for two reasons. First, his work showed for the first time that the laws of physics apply to all objects. The same force that causes a leaf to fall from a tree also keeps the planets in orbit around the sun. This fact had a profound effect on how people viewed the universe. Second, the law provided us with an equation to calculate and understand the motions of a wide variety of celestial objects, including planets, moons, and comets. The gravitational force is always attractive, which is shown here in figure 3. Every mass attracts every other mass. Therefore, the direction of the force of gravity on one mass, such as mass 1, due to a second mass, such as mass 2, points from the center of mass 1 toward the center of mass 2. The magnitude of the gravitational force exerted by mass 1 on mass 2 is equal to the magnitude of the gravitational force exerted by mass 2 on mass 1. Since the forces are both attractive, this result is precisely what we could expect from Newton's third law, which gives us the force of object 1 on object 2 equals negative force object 2 exerted on object 1. The two gravitational forces are an action-reaction pair because they are equal in magnitude and opposite in direction, and they act on different members of the pair of objects. Another important feature of the universal law of gravitation is that the force follows the inverse square law. The inverse square law is a mathematical relationship between variables in which one variable is proportional to the inverse of the square of the other variable. When applied to gravitational forces, this relationship means that the force is inversely proportional to the square of the distance between the mass centers. In other words, the force of attraction drops quickly as the two objects move further apart. No matter how large the distance between the mass centers, however, they will still experience a gravitational force. Every massive object in the universe exerts a force of attraction on every other massive object. If both objects have a small mass compared to the distance between their centers, they will experience a small gravitational force. For the force to be noticeable, at least one of the objects must have a large mass relative to the distance between the object centers. All right, next, let's have a look at the value of lowercase g. On Earth, we can calculate the acceleration due to the force of gravity, g, from the universal law of gravitation. Near Earth's surface, g has approximate value of 9.8 meters per square second. The precise value of g, however, decreases with increasing height above Earth's surface based on the inverse square law, which is shown here in table 1. The value of g also varies on the surface of Earth because the surface varies in distance from the center of Earth. Okay, next let's have a look at how we can calculate the force of gravity. Well, the first measurement of the gravitational constant, uppercase g, was carried out in 1798 in a famous experiment by Henry Cavendish. Cavendish wanted to measure the gravitational force between two objects on Earth using two large lead spheres. He needed to use spheres with a very small distance between them, or he would have found the gravitational force nearly impossible to observe. Cavendish arranged two large spheres of mass 1 and mass 2. Cavendish arranged two large spheres of mass 1 in a dumbbell configuration, and suspended them from their center point by a thin wire fiber, as shown here in this figure, figure 4. He placed another pair of large spheres with mass 2 close to the suspended masses. The gravitational forces between the pairs of masses M1 and M2 caused the dumbbell to rotate. As the fiber twisted, tension in the fiber caused a force resisting the twist that increased as the rotation increased. At a certain angle, this twisting force balanced the gravitational force. By carefully measuring the angle theta, Cavendish could determine the force on the dumbbell as well as separation of the spheres. By also measuring the masses of the spheres and inserting the values into the universal law of gravitation, Cavendish could measure the uppercase G. So through this method, Cavendish measures the value of G, which is approximately 6.67 times 10 raised to the power of -11 Newton square meters per square kilograms. The constant G has this combination of units because it gives a gravitational force in newtons. When you multiply the units of G by two masses in kilograms and divide by square of a distance in meters, you will be left with newtons. Follow his calculation of the uppercase G. Cavendish was able to calculate the mass of Earth. In fact, all masses of planetary bodies can be determined by using the universal law of gravitation. Although Cavendish conducted his experiment more than 200 years ago, his design still forms the basis for experimental studies of gravitation today. Okay, next let's have a look at some sample problems which show how to calculate the force of gravity between two spherical masses, as well as how to calculate the mass of a planet body. Okay, so let's consider this sample question first. The center of two uniformly dense spheres are separated by 50.0 centimeters. Each sphere has a mass of 2.00 kilograms. There are two questions you need to answer. First, calculate the magnitude of the gravitational force of attraction between the two spheres. Then how much of an effect will this force have on two spheres? Okay, according to the formula you have just learned, just here, universal law of gravitation. Okay, you should put this on your notebook. I'll give you 2 minutes or 5 minutes. We'll have a look at this question here, okay? And after that, we'll have a look at the solution together. You can start now. All right, have we finished? Okay, let's have a look at the solution together. So we are given the following information. We know the gravitational constant, uppercase G, is approximately 6.67 times 10 raised to the power of -11 newtons square meters per square kilograms. And also we know the distance between the two spheres is 50 centimeters, which is 0.5 meters. And we also know the masses of the two spheres. M1 equals M2 equals 2 kilograms. So according to the universal law of gravitation, you can calculate the magnitude of the gravitational force of attraction between the two spheres, which is Fg equals uppercase G times M1, M2 over R squared. So put all the values in, we have the magnitude of the gravitational force of attraction between the two spheres is approximately 1.07 times 10 to the power of -9 newtons. So this is a very small number, right? Then we can answer the following question. The gravitational force of attraction between the two spheres is 1.07 times 10 to the power of -9 newtons, which is too small to have any noticeable effect on the motion of these two spheres under normal circumstances. All right, any questions? Okay, if you don't have any questions, let's consider another problem. Calculating the force of gravity and solving for mass. Eris, a dwarf planet, is the ninth most massive body orbiting the sun. It's more massive than Pluto and 3 times farther away from the sun. Eris is estimated to have a radius of approximately 1,200 kilometers. Acceleration due to gravity on Eris differs from the value of G on Earth. In this three-part problem, you will explore the force of gravity on the surface of Eris. First, suppose that an astronaut stands on Eris and drops the rock from the height of 0.3 meters. The rock takes 0.87 seconds to reach the surface. Can you calculate the value of G on Eris? Next, calculate the mass of Eris. Then, suppose that an astronaut stands on Eris and drops a rock from the height of 2.50 meters. Can you calculate how long it will take the rock to reach the surface? Okay, again, I'll give you probably 6 minutes to consider this question first, and then we'll have a look at the solution together. You can start now. Right, let's have a look at the solution together. So the information given here is delta D equals 0.30 meters. And the initial velocity, initial speed VI is 0 meters per second, right? And time taken is delta T equals 0.87 seconds. And we need to calculate the G on planet Eris. So near the surface of Eris, the gravitational acceleration will be approximately constant, like it is near the surface of Earth. We can determine the value of G Eris by using the equation for the motion of an object falling under constant acceleration. Delta D equals VI delta T plus 1/2 times the acceleration times delta T squared. Since we know the initial speed is 0, the equation simplifies to delta D equals 1/2 times the acceleration times delta D squared. So for this problem, we know the acceleration is the number we want, which is G Eris. So choose the direction up as positive direction, and down is negative direction. Then we will have delta D equals 1/2 times A times delta T. Then we can solve the gravitational acceleration G Eris, which is 2 times negative 0.30 over 0.87 squared, which is approximately negative 0.7927 meters per square second. So notice that this is a one-dimensional problem. So the negative symbol here indicates that the gravitational acceleration is pointing downwards. So the magnitude of the acceleration of the gravitational acceleration on Eris, on the surface of Eris, is approximately 0.79 meters per second, per square second. Okay, for the second question here, because we have just calculated the gravitational acceleration G Eris, and we also know the gravitational constant and the distance between the center of the two objects. R is 1,200 kilometers, which is 1.2 times 10 raised to the power of 6 meters. And this time we want to find the mass of Eris. To use the equations for force of gravity, Fg equals mg, and the universal law of gravitation, we have the following relationship. Fg equals gm1 m2 over r squared. So equate these two expressions for the gravitational force on the rock. Then Fg equals m rock g Eris, and Fg equals g m rock m Eris over r squared. And use 1 Newton equals 1 kilogram times meter per square second. Then we have the following relationship. M rock times G Eris should equal G M rock M Eris over R squared. Then the mass of Eris, M Eris, equals G Eris times R squared over the uppercase G. So put all the values in, we have the mass of Eris is approximately 1.7 times 10 raised to the power of 22 kilograms. So the mass of Eris is approximately 1.7 times 10 raised to the power of 22 kilograms. Okay, any questions? Okay, then for the third question, since the value of G Eris is already known to us, we can then use the equation delta D equals VI delta T plus 1/2 times acceleration times delta T squared. This is an equation from the dynamics we have already learned, right? To determine the time it will take the rock to reach the surface. Again, we know the initial speed is 0. So the equation simplifies to delta D equals 1/2 times acceleration times delta T squared. So there is only one unknown quantity in this equation, which we can solve. Delta T is a square root of 2 times delta D over acceleration A. So put all the values in, we have delta T is approximately 2.5 seconds. So the statement is, it would take the rock 2.5 seconds to fall 2.50 meters. All right, any questions? Okay, if no questions, let's consider another problem here. Okay, so as shown in this figure, there are 3 large spherical asteroids in space, which are arranged at the corners of a right triangle ABC. Asteroid A has a mass of 1.0 times 10 raised to the power of 20 kilograms. Asteroid B has a mass of 2.0 times 10 raised to the power of 20 kilograms and is 50 million kilograms. 50 million kilometers, or 5.0 times 10 to the power of 10 meters from asteroid A. Asteroid C has a mass of 1.0 times 10 raised to the power of 20 kilograms, and also we know the distance between A and C, which is 2.5 times 10 raised to the power of 10 meters. So there are 2 questions you need to answer. First, can you determine the net force on asteroid A from asteroid B and C? Then, can you determine the net force on asteroid B from asteroid C? Okay, I'll give you 6 minutes to consider this question by yourself. And after that, we'll have a look at the solution together. So note that this is a two-dimensional problem, right? Okay, you can start now. Right, let's have a look at the solution. So in first question, again, we can use universal law of gravitation to calculate force on asteroid A due to asteroid B first. So let's use the letter FAB to denote this force. Here, FAB, according to the formula, is equals GMA MV over RAB squared, right? So we have all values for the variables on the right side. So just put all the values in, then FAB is approximately 5.336 times 10 raised to the power of 8 newtons. Then use the same method, we can also calculate force on asteroid A due to asteroid C, denoted by FAC. Again, put all the values in, we have FAC is approximately 4.269 times 10 raised to the power of 9 newtons. Note that these two numbers are just the magnitude of the forces. Because forces are vectors, so next we need to add these two vectors to find the net force on the asteroid A. So let's use the letter F net A, the vector F net A, to denote the vector sum of FAB and FAC. Since the force vectors lie along the sides of the right triangle, you can then use Pythagorean theorem to calculate the magnitude of the net force on asteroid A. So F net A is a square root of FAB squared plus FAC squared. Again, put all the values in. We have F net A is approximately 4.3 times 10 raised to the power of 9 newtons. Next, because F net A is a vector, we also need to calculate the direction of this net force. So we can use arctangent to find the theta for these force. Theta equals arctangent FAB over FAC, which is approximately 7.1 degrees. So we can make a statement like this. The net force on asteroid A from asteroids B and C is 4.3 times 10 raised to the power of 9 newtons with direction 7.1 degrees north of east, directed towards asteroid A. So that answers the first question. Any questions? Okay, second question. First, we can calculate the distance between asteroid B and C, denoted by RBC. RBC equals the square root of RAB squared plus RAC squared, which is approximately 5.590 times 10 raised to the power of 10 meters. Then, using the universal law of gravitation to calculate the magnitude of the gravitational force between asteroid B and C. So FBC equals GMBMC over RBC squared. Again, put all the values in. We have the magnitude of FBC is approximately 1.7 times 10 raised to the power of 9 newtons. So as this figure 5 indicates, the net force on asteroid B due to asteroid C acts alongside BC. So calculate the angle that this force makes with side AB. We have theta equals arctangent RAC over RAB, which is approximately 27 degrees. So we can make this final statement like this. The force on asteroid B due to asteroid C is 1.7 times 10 raised to the power of 9 newtons with direction 27 degrees east of south, directed towards asteroid B. Okay, any questions? Okay, so this is a solution for question B. You can have a look at the solution here. Okay, if you don't have any questions, let's have a look at another concept, which is called gravitational fields. The universal law of gravitation tells us that at any point in space surrounding a massive object such as Earth, we can calculate the gravitational force on a second object sitting at that point in space. Earth has a mean radius of approximately 6380 kilometers. So an object that is 10 kilometers above Earth's surface or 90 kilometers from Earth's center will have the same gravitational attraction to Earth no matter which landmass or ocean it is positioned above. A vector exists at every point in space surrounding the central object, pointing toward it and depending on the object mass and the distance from its center, which is shown here in figure 7. The gravitational field of the central object can be represented by this collection of vectors. A gravitational field exerts forces on object with mass. The gravitational force strength is the force of attraction per unit mass of an object placed in a gravitational field, and it equals the gravitational force on the object divided by the object mass. On Earth, the gravitational field strength is approximately 9.8 Newton per kilogram. Notice that this has the same magnitude as the acceleration due to gravity on Earth's surface, and thus has the same symbol G. For spherical objects, the strength of the gravitational field at a distance from the surface is the same whether the mass actually fills its volume or sits at a point in the center. We can therefore use the gravitational force equation as though all of the object mass were located at its center. This is why we measure center-to-center distances, which is shown here in figure 8. To calculate the gravitational field strength as a function of a central spherical mass, we combine the universal law of gravitation with Newton's second law. So let us calculate the acceleration due to gravity G on a small mass and object near surface of a spherical planet of mass m planet and radius r. So we have the following relationship, which is shown here. M object G equals uppercase G times M planet times M object over R squared. Then we can cancel the M object to both sides. This gives us lowercase g equals uppercase G times M planet over R squared. So we can apply this formula to other planets and stars by substituting the approximate values for M planet and R. The value of G depends on the mass of the central body, the distance from that body's center, and the gravitational constant, uppercase G. An object acceleration due to gravity does not depend on its own mass. So next, let's have a look at a problem that illustrates how we can calculate the gravitational field strength. Okay, so let's have a look at this problem here. First, calculate the magnitude of the gravitational field strength on the surface of Saturn, assuming that it is perfectly spherical with a radius of 6.03 times 10 raised to the power of 7 meters. The mass of Saturn is 5.69 times 10 to the power of 26 kilograms. Then determine the ratio of Saturn's gravitational field strength to Earth's gravitational field strength, which is 9.8 newtons per kilogram. Okay, you can start now. I'll give you 5 minutes to solve this question, okay? All right, let's have a look at the solution together. Okay, so according to the definition of gravitational field strength, note that gravitational field strength is just a force of attraction per unit mass, right? Therefore, we know the formula to calculate the gravitational field strength should be uppercase G times m over r squared, right? So specifically in this question, because you're calculating the gravitational field strength on the surface of Saturn, you should use the mass of Saturn. So the gravitational field strength on the surface of Saturn, denoted by lowercase g Saturn, equals uppercase G times m Saturn over r squared. So put all the values in on the right side. We have G Saturn equals 10.438 newtons per kilogram. So the gravitational field strength on the surface of Saturn is 10.4 newtons per kilogram. Any questions? Again, gravitational field strength is just the force of attraction per unit mass. Okay. So in question B, the ratio of Saturn's gravitational field strength is 10.438. You have just calculated that, right? And use this number to divide. Use the ratio between this number and the Earth's gravitational field strength, which is 9.8. Then we have the ratio is approximately 1.1. So the ratio of Saturn's gravitational field strength to Earth's gravitational field strength is 1.1 to 1. Any questions? Okay, so this question just demonstrates that gravitational field strength on the surface of Saturn is only slightly greater than the gravitational force strength on the surface of Earth. Each planet in our solar system has a different gravitational field strength that depends on the radius and the mass of the planet. Next, this table 2, lists the relative values for all the planets in our solar system. You can have a look at that. Okay, now we can take a 10 minutes break, and after that, we'll have a look at the second part of this lesson, in which we'll talk about the orbits. Okay, you can take the break now. Okay, now let's have a look at the second part of today's lesson. So we're talking about orbits. So Radasat 1 and Radasat 2 are Earth observation satellites designed and commissioned by the Canadian Space Agency. These eyes in the skies peer down from orbit, capturing images and data that help scientists monitor environmental changes and the planet's natural resources. Examples of satellite monitoring include detecting oil spills, tracking ice movements, identifying ships at sea, and monitoring natural disaster. So here, this figure shows an image of the Radasat 2. A satellite is an object or a body that revolves around another body that usually has much more mass than the satellite. For example, the planets are natural satellites revolving around the sun. Planetary moons, including the Earth's moon, are natural satellites too. Artificial satellites, on the other hand, are human-made objects that orbit Earth or other bodies in the solar system. As we just mentioned, the Radasat 1 and Radasat 2 are examples of artificial satellites. Another well-known example of artificial satellites is the network of 24 satellites that make up the Global Positioning System, or GPS. By coordinating several signals at once, as shown here in Figure 2, the system can locate an object on Earth's surface to within 15 meters of its actual position. The boat shown in Figure 2 here has a computer-controlled GPS receiver that detects signals from these 3 satellites simultaneously. The system calculates distances based on signal speeds and transmission times. A single satellite can identify the boat's location somewhere along the circumference of a circle. 2 simultaneous satellite signals can pinpoint the location at one of 2 intersecting spots, where 2 circles intersect, with a third satellite and therefore 3 intersecting circles. The boat location can be pinpointed. This is referred to as triangulation. Another example of an artificial satellite in Earth's orbit is a space station, a spacecraft in which people live and work. An example is the International Space Station, or ISS, shown here in Figure 3. The ISS is a permanent orbiting laboratory that supports many different research projects. In the process, scientists are also able to study human responses to space travel and zero gravity, or more accurately, macrogravity. 1 times 10 raised to the power of -6 times the value of g. A microgravity environment is present when any object is in free fall. So when you dive from a dive tower into a swimming pool, you are in microgravity until you hit the water. Similarly, astronauts aboard the ISS are in a constant state of free fall and are thus in microgravity environments. It is important to note that the difference between the macrogravity and the gravitational field strengths, since the value of g at the altitude of the ISS is approximately 8.7 newtons per kilogram. Clearly, there is still a significant gravitational force at that altitude, and it is incorrect to say that the astronauts are in zero gravity. And gravitational force of approximately zero would only occur if you were extremely far away from any mass. So knowledge gained from research by orbiting space stations enables scientists to design spacecraft that can safely transport people through space and perform experiments in microgravity environments. These microgravity experiments can lead to breakthroughs in medicine and chemistry. Okay, when Newton developed the idea of universal gravitation, he also theorized that same force that pulls object to Earth also keeps the moon in its orbit. One difference, of course, is that the moon does not hit Earth's surface. The moon orbits Earth at a distance from Earth's center, called the orbital radius. The orbit of moon about Earth is another example of centripetal motion, which we have already studied in chapter 3. The force of gravity on moon due to Earth is a centripetal force that pulls the moon toward Earth's center. As the moon orbits Earth, the moon has velocity perpendicular to the radius vector. Without gravity, the moon would fly off in a straight line. Without its orbital velocity, however, the force of gravity would pull the moon straight to Earth's surface. The orbital motion of the moon depends on both the centripetal force due to gravity and the moon's orbital velocity. The moon's orbit, similar to the orbits of the planets around the sun, is actually elliptical. We can closely approximate the orbits, however, by assuming that they are circular. This approximation is useful for most problem-solving purposes. To analyze the motion of a satellite in uniform circular motion, combine Newton's law of universal gravitation with a mathematical expression describing centripetal acceleration. Using the universal law of gravitation from section 6.1, we can say that gravitational field strength of Earth with mass me at the location of a satellite at height r above Earth's center is given by this formula. Lowercase g equals uppercase G times me over r squared. Also recall from chapter 3 that the formula for centripetal acceleration based on the orbiting object's speed v is given by this formula. Centripetal acceleration AC equals v squared over r, where v is a linear speed. R is the radius of the motion. For a satellite in a circular orbit, the gravitational force provides a centripetal force. Combining the above two equations gives us this relationship here. Then solving for the speed of the satellite using only the positive square root gives us the linear speed of the satellite v equals square root of gme over r. This equation holds for an orbiting body in a central gravitational field. If a satellite orbits around any other large body with mass m, we can replace the mass of Earth in this equation and generalize it to this equation here. V equals square root of uppercase G times m over r. So this equation indicates that the speed of a satellite depends on its orbital radius and is independent of the satellite's own mass. For a satellite to maintain an orbit of radius r, its speed v must be constant. A communicational satellite in geosynchronous orbit. That is a satellite orbiting Earth with a speed matching that of Earth's own rotation. Geosynchronous orbit is an example of an artificial satellite with a constant orbital radius, which is shown here in figure 4. The orbital period represented by the symbol uppercase T is the time it takes an object to complete one orbit around another orbit. A geosynchronous satellite's orbital speed leads to an orbital period that exactly matches Earth's rotational period. To an observer on Earth, the satellite will appear to travel through the same point in the sky every 24 hours. A geostationary orbit is a type of geosynchronous orbit in which the satellite orbits directly over the equator. To an observer on Earth, a geostationary satellite will appear to remain fixed in the same point in the sky at all times. Okay, next, let's consider a sample problem in which we'll explore how can we use equation for orbital speed in problem solving. Okay, let's consider this problem here. Calculating the speed and orbital period of satellite. The International Space Station, or ISS, orbits Earth at an altitude of about 350 kilometers above Earth's surface. First, can you determine the speed needed by the ISS to maintain its orbit? Next, determine the orbital period of the ISS in minutes. Okay, I'll give you 5 minutes to consider this problem, and after that, we'll have a look at the solution together. All right, let's have a look at the solution together. We have just learned that the speed of a satellite depends on its orbital radius, and it's independent of the satellite's own mass, right? And it's given by this formula here. V should equal the square root of GME over R, where ME is the mass of the planet Earth, and R is orbiting radius with respect to the center of the planet Earth, right? So R should equal RE, which is the radius of the Earth, plus the height of the space station, which is approximately 6.73 times 10 raised to the power of 6 meters. Then put all the values in. We know the linear speed, or the speed of the ISS, should equal 7.698 times 10 raised to the power of 3 meters per second. So the ISS requires a speed of 7.7 times 10 raised to the power of 3 meters per second to maintain its orbit. Then in question B, the distance traveled in one period is 2 pi r, right? The orbital period t is the time it takes for the space station to travel this distance. So it's the distance divided by the speed. So the period t equals 2 pi r over v. We have already know the v is approximately 7.7 times 10 cubed meters per second, right? And put 2 pi r there. That'll give us the period, orbital period of the ISS is approximately 92 minutes. Okay, any questions? All right, no questions. Let's consider another problem here. Okay. So in this question, determine the speeds of Venus and Earth as they orbit the sun. The sun's mass is approximately 1.99 times 10 raised to the power of 30 kilograms. Venus has a orbital radius of 1.80 times 10 raised to the power of 11 meters, and Earth has an orbital radius of approximately 1.49 times 10 raised to the power of 11 meters. Okay, I'll give you 5 minutes to consider this question, and then we'll have a look at the solution together. Again, you can use the equation to calculate the orbiting speed, which is the square root of GM over R, right? All right, let's have a look at the solution. In this question is pretty straightforward, right? So first of all, we can find the speed of Venus, which is denoted by v, which equals the square root of uppercase G times ms, which is the mass of the sun, over the orbiting radius of Venus. To put all the values in, we have VV equals 3.51 times 10 raised to the power 4 meters per second. And then we can use the same method to calculate the speed of the Earth, which is approximately 2.98 times 10 raised to the power 4 meters per second. Therefore, we know the Venus orbits the sun at a speed of 3.51 times 10 raised to the power 4 meters per second, and Earth orbits the sun at a speed of 2.98 times 10 raised to the power 4 meters per second. Okay, so this is the end of today's lesson. If you have any questions, just let me know, okay? Otherwise, please remember to complete your homework and submit them before the deadline on Google Classroom.